In this video, we're going to talk about electron configuration. And in a previous video, we've talked about Bohr's model of the atom, which shows that electrons exist only in specific energy levels. In this video, we're going to talk about what's actually in those energy levels. So each energy level contains subshells, which is a set of orbitals. And each orbital is a place where you can find up to 2 electrons. And when we write orbital diagrams and we represent electron configuration, we typically represent these orbitals as just little boxes. But they're not really little boxes. They're really three-dimensional shapes that were predicted by Schrodinger's equations that you might be able to find an electron outside the nucleus. So the first one we're going to talk about is the S subshell, which consists of just one orbital. That orbital is spherical in shape, can hold up to 2 electrons. In the first energy level, that's all there is. And once there's 2 electrons in that S subshell, well, there's no more room for any more. So essentially the next energy level will start, and it'll start with its S subshell. So that S subshell is, spherical in shape, just like the first one. It's just a little bit further away from the nucleus on average, and then the third one's a little further than that, and they just get further and further away. The P subshell is the second one we'll talk about, and that's a little bit more complicated because each orbital isn't just a sphere, it's really a kind of 2-lobed shape that would lie along either the x, y, or z axes of a Cartesian coordinate system. Separately, they'd be drawn like this, but collectively they come together to form the shape you'd essentially get if you took 6 balloons and tied them together. So collectively, this P subshell can hold up to 6 electrons. So first energy level, like we said, just an S subshell, so it only holds 2 electrons. And that's all there's really room for. In the second energy level, there's 2 subshells. You have the S subshell and the P subshell. So collectively, in the second energy level, you can hold up to 8 electrons. In the third, you get a little bit more room. So you have an additional sublevel that appears. So you have the S with its 1 orbital, the P with its 3 orbitals, and the D subshell with 5 orbitals. Something interesting happens when we start to look at the fourth energy level, and that the fourth energy level's S subshell actually is lower in potential energy than the third energy level's D subshell. And in fact, we'll find that electrons will actually occupy that first. And then after the 4s, it'll go back to filling up the 3d. And essentially, electrons work and fill their way up this diagram that you see right here. Now you can see that it gets kind of messy as you get to the higher energy levels. And we're going to actually represent it differently when we're writing out these orbital diagrams. So when we take a look at the periodic table and how it's arranged, it actually tells us the electron configuration. First, we're going to say normally helium exists over here on a periodic table because chemically it behaves like a noble gas. You'll find that noble gases have a full valence shell, and we'll talk about what that is. So they don't really need to gain or lose any electrons. They're pretty happy the way they are, and they don't really react with anything. But for the sake of today, we're going to move it over to the other side of the periodic table, because really all that's in there is the S subshell. And when we look at how the periodic table is arranged, you have the numbers all the way to the left here representing the periods, but you can see that there's really little blocks that exist. There's 4 blocks. First, we have the S block, which is the leftmost 2 columns. In the middle, we have the D block, where the D subshell is being filled out. And to the right, we have the P block, where you're filling a P sublevel. And down below, you have an F block, which really only comes into play when you're talking about elements that exist in the 6th period of the periodic table or lower. So we'll take a look at how these electrons are actually arranged in some of the smaller elements, and we'll talk about the general strategies for filling out orbital diagrams and describing electron configuration. So the first one we're going to talk about is hydrogen, because it has 1 electron. That first electron is not going to go in the 5th energy level or some higher up place. The Aufbau Principle basically says that electrons will occupy the lowest possible energy orbital that they can, and so the first electron will just go in the first energy level's S subshell. So this is the Aufbau Principle. Oops, hold on 1 second. We'll get back to that. Here we are. So we would describe its electron configuration as 1s1, where the first 1 represents the energy level, the S represents the subshell, and that second 1 that's written as an exponent essentially represents how many electrons are in that subshell. The second, if you have an element where you have 2 electrons like helium, the second electron is going to go in the first energy level S subshell as well. So we designate it as 1s2. You might notice that the arrows are drawn in opposite directions, and these arrows are meant to represent the spin of the electron. So you'll notice that anytime you have 2 electrons in the same orbital, that they're going to have opposite spins. And this is the Pauli exclusion principle in action. Pauli exclusion principle is technically defined as saying no two electrons can have the same quantum numbers, but what that really means is that you just can't really have two electrons that are in the same energy level, same subshell, same orbital, and have the same spin. So they're all going to be going one up, one down if they're in the same orbital. After that first energy level's S subshell fills up, then we have to move on to the second energy level. So the next electron, say for lithium, which has 3 electrons, would go in the second energy level's S subshell. And we'd write its electron configuration as 1s2 because there's 2 electrons there, and 2s1 because you have 1 electron in the second energy level S subshell. Then next you're going to see that we're going to go in that same orbital because there's no other orbital of equal energy. And when we have beryllium, we would have, again, an opposite spin on that, and we would have a 2s2. Once that fills up, we're going to move on to the other side of the periodic table, and we're going to start filling up a p subshell. Notice that on the periodic table shown to your right, you can see that as these are filling up, we're moving along the periodic table, just like you would read, from left to right and top to bottom. So beryllium has 4, and boron has 5 electrons. That first electron goes in the 2p subshell, and it goes in the first orbital. But you'll notice something interesting. We move on to the next element, carbon. You'll see that it doesn't actually go in that same orbital. It'll in fact go into the next orbital, and this follows something called Hunds Rule, which states that each orbital of equal energy will contain 1 electron before any of the orbitals contain 2. And we see that followed again with nitrogen. So we now have 1 electron in each of the 3 orbitals of the 2p subshell. Once that's filled up, however, we're going to have to start pairing them up. So again, they'll have opposite spins, so they follow Pauli exclusion principle. When we look at oxygen, its next electron will go there in the 2p subshell, and it's going to be paired up. Then fluorine will have 1 more, and then once we get to neon, we see that we now have a complete outermost S and P subshell. So this element's said to be following the octet rule. Essentially, atoms all try to gain, lose, or share electrons to become like the noble gases like neon. And essentially, this is a stable configuration that has a very low potential energy situation for the atom. Okay, so now you'll notice, now we move on to the next energy level, we're also starting a new row on the periodic table. If we look at sodium, it's got 11 electrons, so 1 more in the 3s subshell. And you'll notice that all the elements in this group or column on the periodic table, all are going to end in an S1 configuration. Potassium, the next one down, you're going to see is going to end in a 4s1. After sodium, we have magnesium, which is 3s2. And again, you'll note that any element below magnesium or above it is going to end in s2 as well. After we fill up that S subshell, then we have to move on to the 3p subshell. So again, we hop across the periodic table, skipping the middle, and then we're going to go aluminum with 3p1. We'll see that silicon's 3p2, phosphorus 3p3, sulfur 3p4, chlorine 3p5, and argon 3p6. So now again, we've reached a noble gas configuration where we have a full outermost S and P subshell, so this atom is following the octet rule and is very stable and unreactive. Now's where things get a little interesting. So after the third energy level's P subshell fills up, again, we said the fourth energy level's S subshell is actually lower in potential energy than the D subshell. This whole table is arranged by increasing potential energy. As you go up, they become higher in potential energy. So again, you can see the 4s comes before the 3d. Even though it's a higher energy level and technically exists further away from the nucleus in an outer shell, it will fill up before the third energy level's D subshell fills up. These orbitals in the D subshell have higher potential energy, even though they're still buried in an inner shell. So first goes potassium. Again, 4s1 because it's in the first group. And you could predict that anything below this, again, is going to end in an S1 configuration. And in order to become happy and complete like a noble gas, you'll see that all the elements in this group will lose that S electron, so then that what's left is a complete noble gas configuration where it's following the octet rule. Then you would have calcium with 4s2, and then we'd start filling out the D block for these elements that are we call transition metals. So you can see they fill up again following Hunds rule. You put 1 in each before you have 2 in any, and then Start pairing them up in order to complete that D subshell.